Hello everybody, welcome into another lesson. So today we are going to talk about stretching, reflecting, and shifting of graphs of functions. So first we're going to talk about what are called rigid transformations. There are two types of transformations to graphs. You have rigid transformations and you have non-rigid transformations. So first let's talk about rigid transformations. Rigid transformations are those that don't involve changing the size of the graph of the function. So for example, horizontal shifts, vertical shifts, or reflections in either the x or the y-axis do not change the size of the function, of the graph of the function. It may change the location of some of the points, but it doesn't change the overall size. So for a horizontal shift of a graph, you have f of x minus h, which if you set that x minus h equal to 0, that'll tell you how many units right or left you're shifting the graph. And then you have vertical shifts. If you have f of x then plus k, that's a vertical shift. You shift it up or down. So again, you may shift it up or down, but you haven't changed the size of the graph. And then you have a reflection in the x-axis. If you take the negative of f of x, you reflect it in the x-axis. Then if you take f of negative x, you reflect the graph in the y-axis. So those are all examples of rigid transformations. Now we're going to talk about non-rigid transformations. All right. Now, non-rigid transformations, on the other hand, do affect the size of the original graph. So non-rigid transformations can be things such as a vertical stretch, so a vertical stretch involves some coefficient on the f of x. So I have a coefficient a on my f of x where a is greater than 1. If my coefficient is greater than 1 on the f of x, then I have vertically stretched the graph. There's also a vertical shrink. A vertical shrink is when, again, you have some coefficient on the f of x, that a times f of x, but this time 0 is less than a, which is less than 1. If a were exactly 1, it would stay the same size as the original. So you're either going to have a decimal or fraction coefficient, basically, in order for a vertical shrink. And then you have a horizontal stretch. So let's say we have, this time you have f of some constant times x, f of c of x. A horizontal stretch works the opposite of a vertical stretch. If 0 is less than c, which is less than 1, that is a horizontal stretch. And then you have, of course, a horizontal shrink. A horizontal shrink will occur when, again, you have some f of cx. This time that c is greater than 1. If the coefficient of x inside of the f of x is greater than 1, you have a horizontal shrink. So vertical stretches and shrinks, as well as horizontal stretches and shrinks, they're non-rigid transformations because they do affect the size and shape of the graph. And you can have rigid and non-rigid transformations all occurring at the same time. So we're going to go over some examples here, and we'll start with linear. That's probably your easiest one. First we'll graph the parent function, and then we'll apply some transformations to it. So let's say I have f of x equals x. And for a little bit of Friday humor, let's say this is the mother function, which is exactly what it is. F of x equals x, so let me just plot some sufficient points here. So there's my f of x equals x. That's the basic graph of the parent function f of x equals x. The normal graph. Now, if I take it and I apply some transformations, so let's just do a shift. Let's say I do f of x equals x minus 2. If I set x minus 2 equal to 0, I get x equals 2, which means I am shifting to the right 2 units. I am shifting right 2 units. Now, the f of x equals x function is also unique, that you can have a vertical and horizontal shift occurring at the same time. Because f of x equals x, then minus 2, this is also shifting downward 2 units. So it's shifting down 2 units as well. So let's see, at 0 I'll be at x equals 0, I'll be at negative 2. At 2, x equals 2, I'll be at 0. So 2 points should honestly be sufficient for the graph. So there's my graph of f of x equals x minus 2. I've shifted the original function f of x equals x to the right 2 units, and I've shifted it downward 2 units. Alright, now this time, let's say I just make this f of x equals x plus 2. I set x plus 2 equal to 0, I get x equals negative 2. I've shifted everything to the left 2 units. So I am shifting the original graph of f of x to the left 2 units, but I'm also shifting it upward 2 units. So at x equals 0, I'd be at 2. At x equals negative 2, I would be at y equals 0. So now I can go ahead and graph this. And here is the graph of f of x equals x plus 2. I've shifted the original f of x equals x left 2 units and upward 2 units. All right, now so what about f of x equals negative x? So f of x equals negative x, well, I have a negative on my f of x of the original function, right? Negative x is just the negative of f of x equals x. So I definitely have a reflection in the x-axis. And for f of x equals x, if I took f of negative x, I would also get negative x, so you actually have a reflection in the y-axis as well. Linear functions are unique where you can have it occur in both of them. So now let's just graph f of x equals negative x. So 0 At negative 1, you'd be up at positive 1. Negative 2, you'd be up at positive 2. 1, you'd be down to negative 1. 2, you'd be down to negative 2, and so on. So there is my graph of f of x equals negative x. I have literally taken the graph of f of x equals x. I have reflected it in the x and y axis both, and you can see that here. All right, let's do some non-rigid transformations of this. So let's say I have f of x equals 2x. So this time f of x equals 2x. This would be the same as 2 times f of x, right? So I have a vertical stretch of 2. Now, again, linear functions are unique because if I take f of 2x and put it into f of x, I'll end up also getting f of x equals 2x, which means I have a horizontal shrink of 2. So simultaneously, the graph of f of x is being stretched vertically by a factor of 2, but it's being horizontally shrunk by a factor of 2. So let's put in some points and plot this. So still 0, 0, 1, 2, 2, 4. All right, negative 1, negative 2, negative 2, negative 4. Let's go ahead and draw the graph of f of x equals 2x. So what I have done to the original graph of f of x is I've stretched it vertically by a factor of 2. You see it's more vertical, but I have shrunk it horizontally because it's not as close to the x-axis as it was. So that's how a vertical stretch and shrink work. Now let's combine some of these transformations. Let's say I have the negative of x minus 3 plus 5. So what is going on with the original graph of f of x? I have all this going on. Well, I have a negative outside of the parentheses, so that means I have a reflection in the x-axis. We can get that for certain. A reflection in the x-axis is a given. Now, what else is going on here? I have that x minus 3, right? I have that x minus 3. What else is going on? If I take x minus 3, set it equal to 0, I get x equals 3. So I'm shifting the graph of f of x to the right 3 units. Shift right 3 units. Then I have all that plus 5. The plus 5's outside of the parentheses, so I'm shifting the graph of f of x upward 5 units. So I'm going to shift up 5 units. So we know we are taking the graph of f of x, we're reflecting it in the x-axis, we're shifting it right 3 units, we're shifting it up 5 units. So let's see what the heck that actually looks like. So let's see, at x equals 3, you would get a y value of 5. X equals 4, you would get a y value of 4. X equals 5, you would get a y value of 3. X equals 6, you would end up getting a y value of 2. X equals 7, you would get a y value of 1. X equals 8, you get a y value of 0. So we can plot all these and we can draw our graph. So this is the graph of f of x reflected in the x-axis, shifted right 3 units, and shifted upward 5 units. So the transformations you can get from these are truly amazing. Alright, so I think that's enough linear. Let's do a quadratic function. Let's go ahead and do some quadratics. So let's just do f of x equals x squared. The standard parent function f of x equals x squared. We know we're going to get a parabola, right? So 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4. I think we got sufficient points to draw this. So there's your standard graph of f of x equals x squared. A nice parabola. Now, let's do some transformations on this. Let's say I take the quantity of x minus 5, raise that to the second power. So what's occurring with the graph of f of x equals x squared? Because now this is x minus 5 quantity squared. All I have going on is if you take that x minus 5, set it equal to 0, you get x equals 5. That means I'm shifting this to the right 5 units. So this is a shift right of 2 units, of 5 units. Why did I say 2? We're shifting it right 5 units from the original parent function f of x equals x squared. So my vertex will be at 5, 0. At 6, I'll get 1. At 4, I'll get 1. At 7, I'll get y equals 4. At 3, I'll get y equals 4. So I can go ahead and graph this. And this is a perfect example of a rigid transformation. The size of the graph hasn't changed. I've just shifted everything to the right 5 units. That's all I've managed to do. Alright, now let's change it up again here. This time, what if I take f of x squared, f of x equals x squared, then minus 5? So I have a minus 5 outside of the x squared. Well, what's actually happening here? I'm shifting it vertically downward 5 units. So I've shifted the graph of f of x downward 5 units. Which means then when x is 0, I'll get negative 5. X is 1, I'll get negative 4. When x is negative 1, I'll get negative 4. When x is 2, I would get negative 1. When x is negative 2, I would get negative 1. And some point, it would cross the x-axis. Not exactly, well, it'd be the plus and minus the square root of 5 it would cross, but we're not solving this right now, we're just graphing it. So, again, the size of the graph of f of x equals x squared hasn't changed. I've just shifted everything downward 5 units. That's all I've managed to do. Alright, now, what if we do a reflection? Let's take f of x equals the negative of x squared. Well, what's going to happen? You're going to end up, if we take negative x, raise that to the second power, you'll just get x squared. So unfortunately, we can't really reflect an even power graph of a function in the y-axis. We can't do that because if you raise a negative number to an even power, it'll always come back positive and will make that reflection in the y-axis null and void. We can, however, reflect it in the x-axis. If we did f of x equals negative x squared, now we're in business. We have a reflection in the x-axis. So, and that's literally all that's going to occur is a reflection in the x-axis. So let's see, 0, 0, 1, negative 1, negative 1, negative 1, 2, negative 4, negative 2, negative 4. And I think we got sufficient points to plot this, to draw it. So there's my graph of f of x equals negative x squared. Again, the size of f of x equals x squared hasn't changed. I've just reflected it in the x-axis. That's all I've done. All right, let's do some shrinking and stretching here. Now, let's say I have f of x equals, let's see, 2x squared. F of x equals 2x squared. So I have the coefficient on the x squared being 2. This is a vertical stretch of 2. Now, I think we got sufficient points to plot all this, and we can definitely plot this. So 0, 0. At 1, you would actually be at a y value of 2. Same with negative 1. When x is 2, you would actually be all the way up at 8. Same when x is negative 2. So let's plot this. Let's graph it, rather. So as you see, what I have done is I have vertically stretched this by a factor of 2. So that's what I've managed to do. Now, let's say I have f of x equals the quantity of 2x squared. Well, that's going to simplify into f of x equals 4x squared, which would just give you another vertical stretch of 4. So this 2 inside the parentheses would show a horizontal shrink, since the coefficient on the x is greater than 1. But if you take this to the second power, this horizontal shrink would also turn into a vertical stretch. In fact, with all graphs of functions, anytime you have a vertical stretch, you have a horizontal shrink. Anytime you have a vertical shrink, you have a horizontal stretch. So that's something good to keep in mind. All right, f of x equals 1/2 times x squared. So let's graph that. So let's see. That coefficient on the x squared means you have a vertical shrink. In this case, since the coefficient on the x squared is less than 1 but greater than 0, you have a horizontal shrink of 2. It's always of 1/2, I should say. Horizontal shrink of 1/2. Okay, let's graph this. So 0, 0. At 1, you would get 1/2. Same with negative 1. Now at 2, half of 4 is 2. Half of, see, at negative 2, you'd also get 2. And I think we got sufficient points to plot this, to graph it. So yes, I have vertically stretched this. I have vertically shrunk this graph. It's not as tall, but I've horizontally stretched it. It gets closer and closer to the x-axis. That's what I've done. Now let's do one transformation that combines them all. Alright, so what's going on with the original graph of f of x equals x squared? Well, we definitely have a reflection in the x-axis, right? Since the negative sign's outside the parentheses. For starters, we'll have a reflection in the x-axis. Alright. right, what else? Now, go inside the parentheses, you have x plus 3, that quantity squared. If you just set the x plus 3 equal to 0, you would get x equals negative 3. You're shifting everything to the left 3 units. So you're going to shift the graph left 3 units. And then that minus 7 outside the parentheses indicates you're shifting the graph down 7 units. All right. So now let's put all this together here. So your vertex should be at the point negative 3, negative 7. 7. There should be the vertex of the graph. Now, let's say I put in negative 4. Well, negative 4 plus 3 squared, that would end up giving me negative 1 squared, which is 1. I negate that, I get negative 1 minus 7, I'll get negative 8. Likewise, if I put in negative 2, I would get 1 squared, which is 1. Negate that, you get negative 1 minus 7, which is negative 8. And really, this is going to be your graph. It's going to look smaller, but the size of the original graph of f of x equals x squared hasn't changed. I've just reflected it in the x-axis. I've shifted the vertex to the left 3 units, and I've shifted it downward 7 units. So there's the graph of all that. Okay. Let's go on to f of x equals x cubed. This is a good time to review some very basic fundamental graphs that we've learned in algebra. So the typical graph of f of x equals x to the third. So the typical graph of f of x equals x to the third. Well, what does that look like? 0, 0, 1, 1, 2, we're all the way up to 8. Negative 1, negative 1, negative 2, we're all the way down to negative 8. So there's my nice graph of f of x equals x to the third, right? Your typical curve that you see with origin symmetry. Well, let's apply some transformations to this. So there's the parent function, f of x equals x to the third. We're going to apply some transformations. So let's say I take x minus 1 and I raise that to the third power. What's happening here? So now I have the quantity of x minus 1 raised to the third power. Just set x minus 1 equal to 0, you get x equals 1. You just shifted everything to the right 1 unit. So that's a shift to the right 1 unit. So that means my starting point would actually, in this case, be at 1, 0. And then let's see, at 0, I'd be at negative 1. At negative 1, I'd be down to negative 8. Alright, so then at 2, I would be at 1. And then at 3, I would be at 8. So literally all I've done is I've taken the graph of f of x equals x to the third, I've shifted everything to the right 1 unit. That's all I've managed to do. Alright, now let's say I take the graph of f of x equals x cubed, I'd make it x cubed plus 1. So I have a plus 1 outside of the x cubed. What's happening with the original graph of f of x equals x to the third? Well, I'm just simply shifting everything upward 1. So we shifted upward 1. So at 0, I would have the point, y point being 1. At 1, I would get a y value of 2. And then when x is 2, I would get a y value of 9. Alright, let's see, when x is negative 1, I would get a y value of 0. When x is going to be negative 2, I would get a y value of 7. So let's see, here is my graph. And as you can see then, I've just taken the original graph of f of x equals x to the third, I've shifted everything upward 1 unit. That's all I've managed to do. Okay. F of x equals the negative of x to the third power. So f of x equals the negative of x to the third power. So what's happening there? Well, if I take that negative of x to the third power, I'm going to get negative x raised to the third, right? So that initially started out as a reflection in the y-axis. It just turned into a reflection in the x-axis. So as we know, when you take a negative number to an odd power, such as 3 or 5, you get a negative back. So in actuality, I have a reflection in both axes. I have a reflection in the x and y axes. And you're going to see that, and that's a property that's unique to odd power functions. So at 0, I would get 0. Now when x is 1, I would actually end up getting negative 1. When x is 2, I would actually get negative 8. When x is negative 1, I would get a y value of positive 1. When x is 2, I would get, or negative 2, I would get a y value of 8. So let's go ahead and draw this bad boy. So there is my graph of f of x equals negative x to the third power. The size hasn't changed at all. I've simply just reflected it in the x and y axes. That's all I've managed to do. Okay. Let's do some shrinks and stretches. So let's say I take f of x equals 2x to the third. So I have a coefficient of 2 on x to the third. All I'm doing is a vertical stretch of 2. So let's draw this. So when x is 0, you still get 0. Now when x is 1, you get a y value of 2. When x is negative 1, you get a y value of negative 2. When x is 2, 2 times 8 is 16. That's going to be somewhere all the way up here. And same with when y is negative 2, I'll be down to negative 16. I ran out of room to graph, but we can see your graph is greatly distorted because you've vertically stretched this by a factor of 2, which means you've horizontally shrunk it by a factor of 2. So that's something to bear in mind. Now let's go on the flip side here. Let's say f of x equals 1/2 of x to the third. So f of x equals 1/2 of x to the third. Well, this is a a vertical shrink of a factor of 1/2, which is a horizontal stretch also. Vertical shrink of 1/2. Let's go ahead and draw this. So x is 0, you still get 0. When x is 1, you'll get a y value of 1/2. When x is 2, half of 8 is 4, so you get a y value of 4. When x is negative 1, you would get a y value of negative 1/2. When x is negative 2, you would get half of negative 8, which is negative 4. So as you see, yes, I have vertically shrunk this, but I have horizontally stretched it by a factor of 1/2. It's closer to the x-axis. Now let's do one master transformation of this, then we'll move on to the absolute value function. So let's see, f of x equals negative 1/2 times x plus 2 raised to the third power minus 3. Alright, so this is a big change in the original f of x equals x to the third. What's really going on here? You have a negative on that coefficient of 1/2, which means a reflection in the x-axis. So we for sure have a reflection in the x-axis. Now, what's with that negative 1/2? So what's with that 1/2? Let's look at that. That's a vertical shrink of 1/2. What else is another transformation? Look inside your parentheses. The x plus 2 raised to the third power, just set that x plus 2 equal to 0. You would get x equals negative 2, so you're shifting everything to the left 2 units. So shift left of 2. And then you have the minus 3 outside of the parentheses. That means you're shifting everything downward 3 units. So the change from the original f of x equals x to the third to what you see here is a reflection in the x-axis, a vertical shrink of 1/2, then shifting left 2 units and shifting down 3 units. So let's put all this together and graph it. So when x is negative 2, your y-coordinate would end up being negative 3. Right there, okay. Now, let's take x equals negative 1. So that would be 1 to the third is 1. You would get negative 1/2 of that minus 3. You would end up getting negative 3.5. Wait a minute. Yeah, negative 1. Sorry, yeah, negative 1 is 1 to the third is 1 times negative 1/2. Is negative 1/2 minus 3. Yes, negative 3.5. There we go. Yep, I knew I misplotted somewhere. Okay, let's put 0 in. So when x is 0, you would get 2 to the third, which is 8, times that negative 1/2 is negative 4, minus 3, you'd be all the way down to negative 7. Alright, now let's go to the left of negative 2. When x is negative 3, you would end up getting negative 1 to the third, which is negative 1 times negative 1/2. That's positive 1/2 minus 3. That'd be negative 2.5 for your y value. Now what about when x is negative 4? Okay, well, negative 4 plus 2 is negative 2 raised to the third is negative 8 times negative 1/2. That's positive 4 minus 3 gives you 1. So I think now we have sufficient points to draw all this. So yes, we have shifted the graph and we've distorted the size. So here's the graph of this monstrosity right here. Alright, I want to do the absolute value, and let's see, and the square root. That's all I have left. The absolute value function and the square root. So let's see, f of x equals the absolute value of x. So let's graph the parent function f of x equals the absolute value of x. So x equals 0, y would equal 0. X is 1, y is 1, x is 2, y is 2. X is negative 1, y turns into positive 1. X is negative 2, y is positive 2. So the graph of the parent absolute value function is going to be something like this. So there's your graph of f of x equals the absolute value of x, the parent function. Alright, so let's go ahead and apply some transformations to this. F of x equals the absolute value of x plus 5. So we have the plus 5 inside of the absolute value, so what's happening? You set x plus 5 equal to 0, you get x equals negative 5, which would mean you're shifting to the left 5 units. So shift left of 5 units. Okay, so let's go there to x equals negative 5. You would get a y value of 0. X equals negative 4, you would end up getting a y value of 1. X equals 0, you would actually get a y value of 5. Then let's see, x equals negative 6, you would get a y value of 1. X equals negative 7, you would get a y value of 2. I think we got sufficient points to plot this now. So as you see, the size of the graph of the absolute value of x hasn't changed. I've just shifted everything to the left 5 units. That's all I've managed to do with this. All right. F of x equals the absolute value of x, then outside of that absolute value sign, plus 5. So what's happening there? F of x equals the absolute value of x, then outside of that, plus 5. So all I'm doing is shifting the original graph upward 5 units. So we will shift up 5 units. So when x is 0, I'll be at a y value of 5. When x is 1, I'll be at a y value of 6. X is 2, I'll be at a y value of 7, so on. When x is negative 1, I'll be at a y value of 6. When x is negative 2, I'll be at a y value of 7, so on. So I can graph this. And as you see, the size of the original graph of f of x equals the absolute value of x hasn't changed. I've just shifted everything upward 5 units. That's all I've managed to do. All right. Now, this is really important here. F of x equals negative of the absolute value of x. F of x equals negative of the absolute value of x. So what's going to happen here? Well, it's a reflection in the x-axis, right? Because it's outside of the absolute value. So this is going to be a reflection in the x-axis. So let's go ahead and graph what that would look like. X equals 0, you'll get y equals 0. X equals 1, you'll get y equals negative 1. X equals 2, you'll get y equals negative 2. Now, x equals negative 1, you would get a y value of negative 1. X equals negative 2, you get a y value of negative 2. It just keeps on going. So again, as of right now, I haven't changed the size of the graph. I've simply flipped it and reflected it in the x-axis from the original f of x. That's all I've managed to do. Now this is going to be very important here. What if I tried this? F of x equals the absolute value of negative x. F of x equals the absolute value of negative x. Well, since the negative is inside of the absolute value sign next to the x, you would be tempted to say reflection in the y-axis, right? Well, what happens if I take the absolute value of a negative number? It turns positive, right? This would just turn into the absolute value of x. So you really can't reflect the absolute value in the y-axis. It just doesn't work. Unfortunately, you're not going to be able to do that. Alright, now, let's see. I'm going to take 3 times the absolute value of x. So we got 3 times the absolute value of x. So I'm just going to multiply everything by 3. When x is 0, I'll still get a y of 0, but when x is 1, I would get a y of 3. When x is 2, I would get a y of 6. Now when x is negative 1, I'll get a y of 3. When x is negative 2, I would get a y of 6. So here's the graph of f of x equals 2 times the absolute value of x. So this is, yes, this is a vertical stretch of the original absolute value of x. This is a vertical stretch of 3. So there's the f of x equals 3 times the absolute value of x. Now, let's flip this around here. Let's say I have f of x equals 1/3 times the absolute value of x. Well, this time we have a vertical shrink of 1/3. So we have a vertical shrink of 1/3. So when x is 0, you still get y is 0. When x is 3, you would get a y value of 1. When x is negative 3, you would get a y value of 1. And then here's your graph. So here's the graph of f of x equals 1/3 times the absolute value of x. This is a vertical shrink. It's not quite as tall, but it's more horizontally stretched. It's getting closer to hugging the x-axis, so it's more horizontally stretched. Let's also mention something here. Let's say I take the absolute value of 2x. If we remember about properties of absolute values, this is going to be the exact same thing as the absolute value of 2 times the absolute value of x, which would just turn this into 2 times the absolute value of x. Which also proves even more that a vertical stretch is a horizontal shrink, and a vertical shrink is a horizontal stretch. Alright, let's take one graph where we apply several transformations to this, then we'll move on to the last function, the square root function. So f of x equals -5 times the absolute value of x minus 3 plus 2. So what the heck is actually going on here? F of x equals -5 times the absolute value of x minus 3 plus 2. How are we changing the original graph of f of x equals the absolute value of x? Well, that negative on the outside means a reflection in the x-axis. We can ascertain that for sure. We do have a reflection in the x-axis. What else do we have? Now that 5 outside of the absolute value, that's a vertical stretch by a factor of 5. Now that x minus 3 inside of the absolute value, I'm shifting everything to the right 3 units, so we would shift right 3 units. And then we have that plus 2 outside the absolute value, which means we're shifting everything upward 2 units. So we have a lot of transformations from the original graph of f of x equals the absolute value of x to what we got here. So the vertex is going to be at 3, 2. That would be right here. There's the vertex. Now, let's put in some values. When x is 4, the absolute value of 1 is going to be 1 times -5. That's -5 plus 2 is -3. And let's see, if we put in 5, 5 minus 3 is 2. Well, negative 5 times 2 is negative 10 plus 2, that's negative 8. Alright, so now let's see here. What if I put in 2? 2 minus 3 is negative 1. The absolute value of that is 1 times negative 5 is negative 5 plus 2 is negative 3. And then if I decide I'm going to put in, let's see, 1 minus 3 is negative 2. The absolute value of that is 2 times negative 5 is negative 10 plus 2 is negative 8. So here's the graph I am looking for. Whoa, not that steep on this side. Hold on, I butchered it a little bit. So there's my graph of this monstrosity. I've shifted the original graph of f of x equals the absolute value of x to the right 3 units, upward 2 units. I've reflected it in the x-axis, and I vertically stretched it by a factor of 5. So that's exactly what I should get. And I got one more function, one more parent function we're going to talk about. That's the square root function. Alright, f of x equals the square root of x. So that's another parent function. Well, let's see, let's draw this. X is 0, y is 0, x is 1, y is 1, x is 4, y is 2, and it goes like this. So there's your graph of f of x equals the square root of x, right? Now, let's apply some transformations. I have the square root of x minus 2, all underneath the radical. Well, what am I doing then? I set that x minus 2 equal to 0. I'll get x equals 2, so I'm shifting everything to the right 2 units. So we shift right 2 units. So at x equals 2, I'll get y equals 0. X equals 3, I'll get y equals 1. Then at x equals 6, I would get y equals 2. So all I've done to my original graph of f of x equals the square root of x is I've taken everything and shifted it to the right 2 units. Alright. Let's say I have the square root of x, then outside of that radical sign, minus 2. So this time the 2's outside of the radical sign. Well, I'm just shifting everything downward 2 units. So this is a shift downward of 2 units. So when x is 0, I would actually have a y value of negative 2. When x is 1, I would have a y value of negative 1. And then when x is 4, I would get 2 minus 2, which would give me 0. So here's my graph of the function. All I've done is I've shifted the original f of x equals the square root of x downward 2 units. All right. Now these are about to get interesting. Let's say I have f of x equals negative of the square root of x. So f of x equals negative of the square root of x. Well, since that negative sign is outside of the radical, this is a reflection in the x-axis. So we only have a reflection in the x-axis on the original. So let's see, yes, when x is 0, you'll still get 0, but when x is 1, you'll this time have a y value of negative 1. When x is 4, you'll actually get a y value of negative 2, so your graph is going to go like this. So I haven't changed the size of the original f of x equals the square root of x. I've just reflected it in the x-axis. Now, this is where it really is going to matter, though, where I place the negative sign. F of x equals the square root of negative x. Well, what do we know about the square root of negative x? That means our domain can only be x less than or equal to 0. So this is actually going to be a reflection only in the y-axis at this time. So when x is 0, yeah, you'll still get a y value of 0, but when x is negative 1, negative 1 is positive 1. When x is negative 4, negative 4 is 4, square root of that is 2. So there is my graph of f of x equals the square root of x reflected in the y-axis. All right. F of x equals 2 times the square root of x. So we're going to take f of x equals 2 times the square root of x. Well, what we have here is a vertical stretch of 2. All right, so let's just plot this. So 2 times 0 is still 0, but when x is 1, you'll actually get a y value of 2. When x is 4, you would get square root of 4 is 2. 2 times 2 is 4. So there is your graph of f of x equals 2 times the square root of x. I have vertically stretched this by a factor of 2 because it's taller, and I vertically shrunk it because it's not as close to the x-axis. And then, likewise, I could do 1/2 times the square root of x, which would end up being a vertical shrink of 1/2. So x is 0, you still get a y value of 0. All right, but when x is 1, you only get a y value of 1/2. When x is 4, half of 2 is 1. So yes, I have definitely vertically shrunk my f of x equals x. It's not as tall, and I've horizontally stretched it to where it hugs the x-axis a little bit closer. All right, let's do one more problem here, one more graph where we apply a bunch of transformations. So f of x equals -4 times the square root of x plus 3. Actually, no. Let's do 3 minus x. Plus 7. Here's a fun one then. F of x equals -4 times the square root of 3 minus x, all that plus 7. So how does this vary from the original graph of f of x equals the square root of x? We have a negative sign outside of the square root, which means we definitely have a reflection in the x-axis. So take this one piece of the equation at a time. What's that for? Well, that 4 is a vertical stretch of 4, right? So we're vertically stretching this graph 4 units. Now look underneath your radical, 3 minus x. Notice you have a minus x. What does that mean? That means that you actually have a reflection in the y-axis as well. So we have a reflection in both axes. So this time you have a reflection in the y-axis also. Now take that 3 minus x, set that equal to 0. What are you going to get? You'll get x equals 3, which means you're shifting everything to the right 3 units. So you're going to shift right 3 units. Now then you have that plus 7 outside of all this. That means you're shifting everything up 7 units. Alright, so let's put all this to work. We've shifted everything to the right 7 units, so that means my starting point would be, we shifted it right 3 up 7, so my starting point should be at the point 3, 7. Alright, now what do we got here? Let's put in, let's see, so x would have to be less than or equal to 3. So if I put in x equals 2, I get the square root of 1, which is 1, times negative 4 is negative 4 plus 7, that's 3. So when x is 2, I'll have a y value of 3. Now, let's say I put in negative 1 for x. What am I going to get? I would actually end up getting 3 plus 1, which would be square root of 4, which is 2. So negative 4 times 2 is negative 8, plus 7 is actually negative 1. So at negative 1, I'll have a y value of negative 1. So yeah, here's going to be a real hot mess. Whoops, it doesn't continue there. That's where it starts. I don't need the arrow. Alright, so here's my graph of the original square root of x, f of x equals square root of x, reflected in the x-axis, vertically stretched by 4, reflected in the y-axis, shifted to the right 3 units, and shifted upward 7 units. So what a mess, huh? It almost looks like a completely different function from the original. But yes, that is it for shifting, reflecting, and stretching graphs. Next lesson, we're going to talk about combinations of functions. So I hope everyone has a great night. Take care.